Have you ever noticed how pushing harder on a tap causes more water to flow? That's exactly what voltage does in an electric circuit. It pushes charges to flow. Back in the year 1828, Georg Simon Ohm discovered a beautiful relationship between voltage and current, long before electrons were fully understood. Ohm's law states that the current flowing through a conductor is directly proportional to the voltage across its ends, provided the temperature remains constant. This means voltage equals resistance multiplied by current spelled out, V equals R times I, where V is voltage in volts, R is resistance in ohms, and I is current in amperes. The unit of resistance is the ohm, spelled OHM, and written using the symbol omega. Resistance depends on the type of material and the size of the conductor. Now let's explore what affects resistance. First, if you increase the length of a conductor, electrons face more collisions while moving, so resistance increases. We say resistance is directly proportional to length. Second, if you increase the thickness or cross-sectional area of a conductor, electrons get more space to move, so resistance decreases. We say resistance is inversely proportional to area. Combining both, the formula becomes resistance equals resistivity times length divided by area, spelled out R equals rho times L divided by A, where R is resistance in ohms, rho is the resistivity of the material, L is the length in meters, and A is the area in square meters. Imagine two wires, double the length, and resistance doubles. Halve the area, and resistance also doubles. Let's now bring these ideas together. Start with Ohm's law. V equals R times I. Substitute R from the previous formula. R equals rho times L divided by A. So now we get V equals I times rho times L divided by A. Rearranged for current, it becomes I equals V times A divided by rho times L. This tells us that current increases when voltage or area increases and decreases when resistivity or length increases. In simple terms, more push and more space give you more flow. More resistance or longer path slows the current down. Let's now look inside the wire at what's happening per unit area. Current density, denoted by capital J, is defined as current per unit area. So, J equals I divided by A. Also, the electric field across a conductor of length L is E equals V divided by L. Now, from the full version of Ohm's law, we already have V equals I times rho times L divided by A. When we substitute and simplify, we get E equals rho times J, or we can write it as J equals sigma times E. Here, sigma spelled sigma is called conductivity, and it equals 1 divided by resistivity. In a visual diagram, both vectors electric field E and current density J point in the same direction inside the conductor. Let's take this relationship and plot it. For materials like copper or aluminum, if you plot voltage on the vertical axis and current on the horizontal axis, you get a straight line through the origin. That's a perfect example of an ohmic conductor, one that follows Ohm's law. But some materials behave differently. For example, in a filament bulb, as temperature rises, resistance increases. In a diode, current flows only in one direction. In these cases, the voltage-current graph is curved, and these are called non-ohmic conductors. The diagram shows two curves, a straight one for ohmic conductors and a curved one for non-ohmic devices like bulbs or diodes. Let's apply Ohm's law in a practical problem. A copper wire has a length of 2 meters and a cross-sectional area of 0.5 millimeters squared. Its resistivity is 1.6 into 10 to the power minus 8 ohm meter. A voltage of 3 volts is applied across the wire. We'll calculate its resistance and the current flowing through it. Step 1. Convert the area to square meters. 0.5 millimeters squared is equal to 0.5 times 10 to the power minus 6. Step 2. use the formula R equals rho times L divided by a substituting values. R is equal to 1.6 times 10 to the power minus 8 multiplied by 2 divided by 0.5 times 10 to the power minus 6. This gives R equals 0.064 ohms. Step 3. Apply Ohm's law. I equals V divided by R, so I equals 3 divided by 0.064, which gives I equals approximately 46.9 amperes. That's a large current because copper has very low resistivity and we are using a thick wire. Let's quickly summarize what we've learned. Ohm's law says that voltage equals current multiplied by resistance. Spelled out, V equals I times our resistance depends on the material, length, and area of the conductor. Spelled out, R equals rho times L divided by a current density J and electric field E are related by E equals rho times J, and also J equals sigma times E, where sigma is conductivity. If the voltage current graph is a straight line, the material is called ohmic. If the graph is curved, the material is non-ohmic. This simple law, discovered over 150 years ago, still forms the foundation of everything from phone chargers to giant power grids. In the next session, we'll dig deeper into why resistance exists and how the drift of electrons explains it at the microscopic level. See you there.